Yeah, it's coming up. So energy systems optimization is a hard problem. We are talking about heterogeneous physics. We are talking about different spatial temporal scales. And how do we approach this typically in practice is through physics-based modeling. And the good news is that we know the fundamental physics of most of these engineering systems. And we can build high-fidelity digital twins. But on the downside is that they are typically computationally very expensive in a forward simulation, and even more so for closed-loop optimization and control. And this creates a lot of scalability issues and a lot of software integration issues from practical engineering perspectives when it comes to real-time decision-makings for sustainable energy systems. So one of the specific examples I want to walk you through is a practical deployment of high-fidelity molecular control in real-world office building in Belgium. That was done during my time at KU Leuven as a postdoc with Lieve Helsen at the mechanical engineering department, where we spent 2 years in developing high-fidelity building models and molecular control to optimize operations of heating, ventilation, air conditioning systems in buildings. And you may ask why we would like to do that, why it is relevant. Well, the buildings globally use over 40% of the energy. And in the US alone, 70% of the electricity goes to residential and commercial buildings. And with the rise of the growth of the data center, this percentage will grow even further. And the problem is that the current controls in buildings are very simple rules and proportional integral derivative controllers that are very inefficient. That creates a lot of energy waste, a lot of overheating, overcooling in times that it shouldn't be really happening. So on the upside of these advanced control technologies in academia, in practical tools, we have the capability to highly optimize these systems. And in this specific case study that was running several months in the field, we have been able to save over 50% on the energy bill, and at the same time improve thermal comfort in the building occupants. But on the downside, this project took over a year and an army of PhDs to deliver. And the reason was, in the modeling and simulation layer, where we spent half a year just building the high-fidelity digital twin using Modelica language, and then we have this high-fidelity model, but it's not really tailored for control, so we had to develop a second model that is control-oriented with linearizing and decomposing the system into different pieces, and design optimal control strategy using Gurobi and MATLAB optimization libraries, then use the machine learning models for forecasting our disturbances, and then stitch it all together with functional MATLAB unit in this horrendous software project that took 1 year to build in order to actually deploy this in real-time decision-making on the cloud by hacking the building management system with the help of the control system vendors. So it was obvious that we cannot really commercialize this technology. Even when we talk with several building automation companies, they are saying to us that, okay, we don't have the manpower, we don't have the necessary expertise to deploy this in the field. So what are the actual bottlenecks when it comes to deploying these advanced control technologies that have been developed and are in practice in aerospace, automotive, and process control industries in the energy systems? Now, the first one is that the building toolkits are heterogeneous, and high-fidelity digital twins are not control-oriented, while the black box machine learning models, they typically don't have guarantees. So we're typically restricted to relatively simpler reduced-order gray box models. The second challenge is that we are solving heterogeneous problems. We are solving real-time optimization for constrained decision-making. We are solving forward simulation models for the complicated heat transfer, including all the nonlinearities. And we are typically solving some supervised machine learning for forecasting. And we need to stitch these together. But these methods and theories have been developed in different communities. And all the software toolkit is very heterogeneous. So we have different tools for constraint optimization and control, different tools for solving our differential equations, and different tools for machine learning. And this was historically like separated silos that have been quite complicated and laborious to integrate in end-to-end software stack. But what is exciting opportunity I see in academia is the confluence of these two domains. Machine learning community, computer science community, bringing wonderful tools that enable automatic differentiation at scale and democratize these toolkits through user-friendly APIs, and more ideas from constraint optimization, dynamic systems being embedded in these machine learning toolkits. And we call this scientific machine learning or physics-informed machine learning that enables us to do so and brings us two major benefits. One, we can learn with way fewer data because we are having fewer degrees of freedom in the model. And we can enforce certain properties like safety or physical quantities like dissipativity or energy conservation in applications when we know that we have these. So we don't need to discover them from data. And there are a lot of different domains that are already working in this broader field of scientific machine learning that is emergent and growing very fast. Here are a few papers that I want to highlight that influence my thinking in this area. Is incomplete and biased literature review, but this kind of sample a few things in physics-informed neural network for PDEs, learning to optimize, learning models, which is typically nonlinear system identification area, and learning to control. And what I want to argue today, that even though these different methods have been developed by operational research community, machine learning community, controls community, or applied math community, they are really the instance of one higher abstraction of problems. So we can call scientific or physics-informed machine learning. And when you look at each of these papers, they can be abstracted in the four major components. And the first one, obviously, is data. We need some form of active sampling or data acquisition to sample our parametric uncertainty scenarios or gather the time series data for system identification. We have some machine learning function approximator, some surrogate model that approximates our unknown relationships in the model. And then the critical component is a domain prior. That can be either your known differential equations, or it can be the structure of your state space model. Or it could be constraints in your optimization problem, then you embed in this computational graph. And the last component is physics or domain-informed loss function, where those quantities that you cannot enforce as a hard structural constraints or treat as implicit layers, you enforce as form of soft constraint penalties through residual learning. And there is, again, whole field of collocation-based methods in dynamical systems that can cover these type of approaches. And I would also argue it's nicely linked with stochastic optimization in OR. Okay, so to give you a quick walkthrough of the major approaches in scientific machine learning, everyone knows physics-informed neural networks, or PINs in short, that have been used for both forward and inverse modeling, mostly for scaling inference for PDEs. So they come with several advantages. They are mesh-free, so you don't need to construct your finite discretization beforehand. You can sample with finer samples for offline training and then query your solutions only at the spatial temporal points when you need. And at the inference time, you're typically getting orders of magnitude acceleration because you are approximating the solution in the learned function approximator, typically neural network. So how do these components look specifically? Well, the data set are collocation points in spatial temporal coordinates. So here's a simple example. You have temporal domain, spatial domain, and you sample these points that you query your neural network model to generate candidate solution that aims to satisfy your partial differential equation. That's the next layer. So you embed this PDE as a layer in your computational graph. For that to represent the PDE that is dependent now on the neural network solution, you need to compute these partial derivatives, but thanks to wonderful and scalable automatic differentiation toolkits. We can compute them rather efficiently. And now you construct your pin loss function, which is nothing else as empirical risk minimization on this PDE equality constraint, and potentially some supervisory loss function that you typically impose on your initial and boundary conditions. So this is a vanilla pin. And there is a lot of research in advanced architectures. How do we sample these collocation points? How do we quantify errors? How do we weight the relative terms in this multi-term loss function? But here I just want to show you this vanilla approach and show you that conceptually it's very similar, or basically the same as learning to optimize in self-supervised setting. That is really emerging area in operation research, power systems optimization that has a huge potential in improving our real-time decision making. Of course, when we are talking about power systems, these are safety critical systems. So if you are having some residual errors in pins for PD solutions, they don't cause any catastrophic failures. But any errors or potential constraints violations in power systems can cause catastrophic failures. So a lot of research in this domain is in so-called feasibility restoration layers. So how do we correct the solutions generated by this neural network to satisfy hard constraints? And conceptually, the method is, again, very similar than pins. But here, instead of spatial temporal coordinates, we sample some parametric space that can represent initial conditions or some stochastic uncertainties in your problem. And your neural network now tries to replace your numerical solver by mapping these parametric scenarios into the primal solutions of the optimization problem that in general form is described by some cost function over your primal decisions parameterized by the uncertainties and some general inequality constraints. So how do we embed the domain awareness in this self-supervised learning to optimize? Well, if your objective functions and constraints are differentiable, ideally smooth, so you can embed them as a layer and evaluate their violations in the loss functions through the same empirical risk minimization that we use in pins. But if you want to have further hard constraint guarantees, again, a lot of research is in these feasibility restoration layers that can be done either through differentiating through optimization solvers, through implicit function theorem, or differentiating to unrolled fixed point operators, projections, or Newton-type solvers. So a lot of exciting new research done even in this community here in this learning to optimize method. The next category of models that I would argue is, again, related and could be formalized on the high level as the same class of problems is nonlinear system identification with constraints. And here, instead of sampling some parametric scenarios or uncertainties or spatial temporal coordinates, we assume some time series data from which we want to learn. And one methodology that is really standing out is neural differential equations that have been being used extensively in generative AI. But here I want to think about neural differential equations from the perspective of engineering applications. Can we utilize these methodologies in modeling engineering systems subject to constraints? And again, apply them in safety critical systems like power systems or heat transfer energy systems modeling. So how do we think about constructing those data sets? They are typically batches of trajectories, which we assume over finite horizon, typically on discrete types time samples. And now the combination of your function approximator with the domain prior comes in different shapes and forms. There is a lot of nonlinear system identification methodologies in the literature that utilize either neural networks or polynomial basis functions in differential programming setting in different shapes and forms. So in the black box neural ODE setting, your right-hand side is represented by neural network, and you differentiate to the ODE solver either by unrolling the operations of the numerical integrators or like RK4 or using adjoint sensitivity method. On the other hand, operator-based approaches like deep Koopman operator, they embed the observables into the latent space through neural network encoding, and in the higher dimensional latent space, they evolve the linear operator and then project it back to the observable space with this type of approximate inverse encoder-decoder architectures. A lot of interesting theory and interesting properties for control in this space. Other approaches like sparse identification of nonlinear dynamics, or SIMD for short, are also used for model discovery. So what I'm arguing here, we can train all of these with stochastic gradient descent based on this empirical ROSC minimization of the trajectory matching for dynamical systems as well. And now when you have capability for modeling dynamical system, when you have ability to handle constraints either structurally or through these implicit layers, you put them together and you can train closed loop dynamical systems to solve certain control tasks. And this is the methodology that we have been developing with my colleagues at the Pacific Northwest National Lab that we call differential priority control, that combines this idea together. And again, we are based on sampling-based collocation approaches of the parametric scenarios in optimal control problem. And we represent the closed-loop system with some function approximator for the control policy, most commonly deep neural nets, and system dynamics representation, either with familiar state space models or known differential equations or learned neural differential representations. Of course, there needs to be some assumptions on the well conditioning of the system, because now we are unrolling this system, which can create rather deep computational graphs. So conditioning of this dynamic system is very, very crucial. But from the higher level methodological perspective, you are solving, again, empirical risk minimization by sampling the scenarios in your parametric space that can be initial conditions of this problem, or they can be conditioning of your constraints or objective functions like different desired reference trajectories to solve this parametric optimal control problem approximately by training this deep neural network. So for those of you who are familiar with control theoretic approaches like model priority control, it's an approximate approach to solve explicit model priority control that traditionally is being solved with multi-parametric programming, but unfortunately the multi-parametric programming approaches don't scale very well because they blow up in complexity of all possible combination of active constraints. So how you can think structurally between this differential priority control and traditional implicit MPC. So it is a simple example on linear model priority control. When we have linear state space model and quadratic cost, where we want to match our desired reference trajectories with our state trajectories. And we can conveniently represent the system state evolution over finite horizon with this type of like lower triangle matrix, where A matrix is my state transition matrix, B is my input dynamics matrix. So when you think about it structurally, it's nothing else as a recurrent neural network. Yeah, when you unroll it as a computational graph. And if you replace the decision variable to be your control sequence, like it is done in online model priority control with explicit control policy, now we have this closed loop neural dynamical system where the policy is represented by the neural part and encodes the explicit control policy approximately. And it can be trained in a batch over distribution of desired reference trajectories and initial conditions. Okay, so that's a high-level overview of different methodologies in scientific machine learning that I'm arguing that are family of this high level of abstraction that we can call scientific or physics-informed machine learning. They come with these four major building blocks, and because of this abstraction, it allows us to build user-friendly software tools. And that's what I have been doing for last already 5 years, together with my colleagues at Pacific Northwest National Lab, by developing the library that is called Neuromancer, which is built on top of PyTorch. And really the vision is to enable a software toolkit that is integrating all of these advancements. And the focus is on modularity, simplicity, and user experience rather than on performance. We chose PyTorch as our backend consciously because of the large community and robust support from the hardware accelerators. And From the front end, the API is modeled based on algebraic modeling languages that we commonly use in controls and optimization, like JUMP or CVXPy or YAMLib, that allow you to formulate the high-level constraint optimization problems or optimal control problems in convenient symbolic abstractions by defining the variables. And on these variables, you symbolically define your objective expressions or constraints. And then you plug them in together in a problem. And in traditional algebraic modeling languages, this problem is parsed into solver-specific form. And then you solve it with interior point or Gurobi or other solvers, Skip, Baron. But here, what we are doing is that we combine this with these machine learning components that are being trained through stochastic gradient descent in PyTorch. And through our problem constructor, we generate this custom computational graph of scientific machine learning components. Whether it is for pins or learning to optimize for learning to control, you have the same standardized API. And really the vision is to be interoperable. So once you train a pin and you have approximation of the PDE and you want to do PDE constraint optimization, you can embed it in learning to optimize. Okay, so that's the software capability that has been developed with my wonderful colleagues at PNL, funded with US Department of Energy. So I want to acknowledge all of their hard work and commitment to making this tool open source and maintainable. Next, I want to highlight two applications that we have been working on. And buildings has been something I was been working for 10 years, which has been already a long time, and we are still not really like solving these problems in real life. But I hope that these type of new tools and capabilities could mitigate some of those engineering problems in the practice, because we don't really have problems with theory. We have problem in making the theory and wonderful numerical tools to be easily usable and scalable in practice. And that's what we are trying to demonstrate in our more applied research, where we want to show that we can now train these control policies through scientific machine learning with surrogate models at the fraction of the time investment and also expertise investment. Because if you have an engineer that now is capable in the scientific machine learning functionality, you don't need to have one expert in modeling, you don't need to have one expert in optimization control and another expert in ML and stitch all of their software solutions together in functional mockup units or in other ways. So that's the argument here. And in the building space specifically, we know a lot of physics, and we can exploit this in these data-driven machine learning surrogates, these physics-informed ML models. We know the buildings are thermodynamically stable systems. They are dissipative. They want to get to the equilibria with the environment. So we can encode those properties in our neural ODEs or neural state space models. We also know that their partial derivatives need to satisfy certain properties with the environment. So if I'm increasing the temperature in this room, the heat transfer through the walls, we also increase temperature in the other room, or not the other way around. So there are a lot of physics constraints that we can embed in these models to reduce the degrees of freedom and allow us to learn from smaller and less excited data, because there's also one of the big problems in industry. Like when a lot of your data is coming with missing data points, low fidelity data, and operating really close to steady states. So how do we solve this problem without physics? Well, we need to really utilize a lot of physics in order to have any like data-driven modeling here. So it's more like data tuning of the physics models rather than large data set machine learning. And one of like very early prototype type of applications which we are exploring is learning to control, learning to optimize for power systems, where we want to reuse all of the software infrastructure that we built for the buildings application and apply it in a different context. So here is, again, small scale example on NIDA system where we know some physics, we know the stability conditions that we can embed in our model. In this case, we have chosen this deep Koopman operator that was physics inspired and constrained to be stable operator. that allow us to train these explicit control policies offline with this empirical ROSC minimization. From the computation perspective, what you are getting is that you are basically offloading your computational effort from the online to offline. So it takes some time, maybe you require some GPUs to train these models offline, but at the online inference, we are typically getting orders of magnitude faster acceleration. And in our papers and others, we are getting up to 5 orders of magnitude acceleration compared to nonlinear optimization solvers like interior point. So that's very, very exciting. But a lot of problems remain. I will talk about 2 specific problems today. There are many, many more, including differentiability, well-conditioning, and convergence of these methods. But I want to highlight 2 more of the structural problems that are common in applications, whether it is power systems or HVAC systems in buildings. The first, we have differential algebraic equations describing the system, where the algebraic equation can represent some energy or mass conservation property, very common in power systems and buildings here. Like a very simple example, when you have the reservoir and then you have a pump, and now the mass is distributed through this three-way valve into 2 tanks. Well, there needs to be some mass conservation at this point. And that's represented by these algebraic constraints on your dynamical system. So how can we train these models and discover their components from data? That was the question that we asked with the colleagues at PNL, and took inspiration from a lot of recent advances in neural differential equation, especially structured differential equations and learning for what is called universal differential equations. I believe this is a term coined by Chris Rakaukas here from MIT, who has been working on these methods for a while. So here we ask the question, like, if we can represent our dynamical system in an operator splitting scheme, which is typically used for large-scale systems, we can apply these traditional fractional stable, or what is called operator splitting schemes, by first solving the one part of the problem, get the update on the dynamical system, the state update, and then use it as initial condition for another initial value problem for the second operator B. So that's like standard operator splitting scheme. And what we ask, like, okay, can we think about this differential algebraic equation and apply the same operator splitting scheme in this context? The answer is yes, but only for certain type of systems, of course. So the type of systems is the index 1 differential algebraic equations, where you can reduce these DAEs into ODEs by differentiating your algebraic constraints exactly once. And for that, we have this Picard-Lidendorf theorem that is telling us what properties do you need to have in order this problem to have unique solutions. So it's basically your differential equation is smooth and the algebraic equation is invertible. So if this holds, then you can apply this relatively simple explicit scheme, this operator splitting, where we introduce algebra solver, H, that takes your differential states, algebra states, and some potential exogenous inputs to get you update on the algebra solution. This can be either Newton solver, or it can be trained as a soft constraints with pins. And then you take this updated algebra state and plug it in your forward ODE. And that's it. Really, like, super simple, trivial kind of a solution for having this neural ODE with algebra constraints that you can think from the computational graph perspective. You get some initial condition, control action that first goes through the algebra solver, solves the algebraic update, and then this algebraic update initializes the ODE solver to get you the differential state solution. And this can be trained again with the same empirical risk minimization on the trajectory matching for both differential on algebraic states. A lot of different and exciting extensions are already in the literature where instead of this explicit scheme, you can have semi-explicit scheme where you first solve the ODE solve and then you project on the algebra or reformulate the whole problem as a nonlinear optimization problem and solve it with IP-opt. So different directions exist. The one is worked by Chris Rocko's group and another one with Lawrence Bigler at CMU. So we are seeing a lot of exciting opportunities in learning for differential algebra equations, tremendously important for industrial applications. So toy example to illustrate the idea where we have this two-tank system and the three-way manifold and the pump from the reservoir. We don't need to represent everything as a black box. We know a lot of structure from this problem, and the underlying differential equations are described by the ratios, where this phi equation is basically height area function that we may not know. So we want to approximate these. And then we have these basically conservation laws on the three-way valve, and we know that the tanks are basically at the same level, so their levels need to like level up because of the gravity. So what we can do, we can enforce a lot of those structural constraints just by knowing the problem. Like this conservation law can be represented by a simple convex combination. And by doing so, we can enforce some of the constraints as a hard architectural constraints rather than soft constraints in the penalties. And this allows you to not only fit the measurement data, but also to respect those conservation laws, which is really helpful for extrapolation out of distribution data, where you can change different design parameters, but your model still respects those physical constraints. So yeah, this is something that I'm very excited for the inverse modeling and real practical applications in energy systems. Yeah, acknowledging all my wonderful collaborators and again, funding of the US Department of Energy that enabled this research on neural differential algebraic equations. And now I want to pivot to the second challenge that we have in energy systems optimization, and it's to handle mixed integer decisions, because all of the scientific machine learning is mostly focused on continuous spaces for natural reasons, because we are using automatic differentiation as a workhorse to compute our gradients. But a lot of practical problems in power systems like unit commitment problem or data center cooling, chiller plant optimization, HVAC systems in buildings have integer decisions, switching between different modes or dispatching different units. So what are the challenges in current landscape of machine learning based optimization? The first one is many of the methods, particularly in machine learning for mixed integer, are based on supervisory signals. So the supervised learning requires you to generate a lot of training data by solving a lot of MIP problems, which are expensive. So that's the first problem. So for this reason, we said, okay, let's focus on self-supervised learning approaches. Second problem is when you are using neural networks as a surrogate policies for solving constraint optimization problems, they are continuous. How can we enforce hard integer constraints without losing differentiability? So we have been focusing on this question, how can we come up with mixed integer surrogates for these control policies that retain differentiability through smooth gradients. And the third one is how do we guarantee feasibility once we train these models, important for any safety critical applications. So yeah, here we've been focusing actually on extension of gradient-based projection that had been proposed by Priya in her paper in DC3, have been really great inspiration of this particular work. And I want to walk you through the pipeline of this self-supervised learning to optimize for mixed integer programming. So we assume, again, empirical risk minimization of some nonlinear objective functions where x is my primal decision variables and psi are those scenarios of problem parameters that I'm assuming I'm sampling from some known distribution. And if I know, let's say, operation constraints of my energy system, then this is relatively cheap thing to do. The constraints, we assume general, nonlinear constraints, smooth and differentiable. And for the policy representation, let's have a mapping phi that maps these problem parameters to primal decisions. So this is up to now standard learning to optimize that you train on this empirical loss minimization of your cost and constraint penalties. How can we embed these mixed integer constraints? So what we introduce are two components. One is called integer correction layer that does the integer rounding while retaining the gradients for end-to-end trading. And the second one is this feasibility projection that utilizes the gradients from the integer rounding in the gradient-based updates. So let's focus on these integer correction layers. Here, the inspiration comes from primal heuristics in mixed integer programming that is called relaxation enforced neighborhood search, or RENS in short. And in RENS, what we do, we have mixed integer program, and we first solve continuous relaxation. Then we obtain these continuous primals, and we get the nearest integer bounds, lower and upper bound, to tighten the subsequent MIP solution. So what we ask here is, can we come up with trainable end-to-end RENS-type layers in learning to optimize? And short answer is yes. And basically what these differentiable integer correction layers do, they are learning to round up or down for some fractional value. And they are learning with respect to this empirical loss minimization of your optimization problem that includes the constraint penalties. So what happens that you are basically learning these conditional rounding mechanisms for specific formulation of the parametric mixed integer program. So how do we do it technically is, okay, we assume that we get initial relaxed solution that can come from continuous neural network or other means, the parametric instance, and the second neural network, this delta, that is taking those instances and gives us these hidden states. And these hidden states basically acts as the corrections. For the continuous variables, they add basically as additive term to correct those continuous variables in the forward pass. And for the integer part, we first round down the fractional value and then treat this integer hidden value through two mechanisms, either what we call rounding classification or learnable threshold. They are practically equivalent. They are just trying to get us this threshold for these indicator functions to decide whether we should round up and down. So one is implemented through a scaled sigmoid layer, and another one with a Gumbel sigmoid that introduces a little bit of stochasticity. But the good thing about these functions is that they are smooth, and we know analytically they're Lipschitz constants, which will be very important for the theoretical analysis of these integer layers in projection mechanisms. Good, so that's the integer correction layer, allows us to round forward in the pass with this hard rounding and retains differentiability thanks to the smooth approximations of the rounding threshold. And how we deal with this indicator function, we just ignore it in the backward pass through straight through estimator. We basically treat it as identity. So that's kind of a trick for differentiability that has been used in machine learning for a long time. Okay, some small example to illustrate how these layers would work. Let's say you have some parametric problem where A and B is a parameter for objective function and constraint, and it is feature for your first continuous relaxation of the problem that gives you these relaxed primals. And then you take those relaxed primers together with those parametric instances in the second neural network that gives you these hidden states. And the hidden state for the continuous variable we just use for directly updating the continuous variable. And the hidden state for the integer variable, you either run through this Gumbel sigmoid layer or scaled sigmoid layer to give you the threshold value for rounding up and down. And you train this end-to-end with this empirical risk minimization of your objective and constraint violations. So that's the kind of learning this conditional rounding for this class of problems. So it's not like general rounding for any problem. You will train the rounding mechanism for your specific problem to favor feasibility. But there are no feasibility guarantees as such in this integer rounding with empirical risk minimization training. So the question is, how can we enforce this feasibility? And here is the inspiration from the DCT type projection that we can also think as alternative to feasibility pump heuristics that is used in mixed integer programming that again alternates between rounding and projection. So again, you solve a continuous problem, you round to the nearest integer. If it is infeasible, you solve projection problem again on a continuous space, and you iterate, yeah, until convergence. So here we again ask questions: how can you utilize this integer correction layers, that RENS type mechanism, in the context of gradient-based updates? And the mechanism is very straightforward. We assume that we have this initial relaxed solution, we have the parametric instance, and we have this pre-trained correction layer. So that acts basically as a transformation of this relaxed solution to the mixed integer solution, and then we use this mixed integer solution to evaluate our constraint violations. And it can be done with L1, L2 penalties. You get basically this scalar energy function for the constraint violations. And if it is 0, okay, you terminate. If it is non-zero, you basically run gradient descent on this function, but on the continuous variable, not on the integer variable here. So basically, you have this composite function, this penalty, and the integer correction layer that you're differentiating through to update the continuous variable. And this was really like important from empirical perspective to get us robust performance from this algorithm. We are still like trying to theoretically understand why it is so. And one of the potential explanations could be our convergence analysis that is based on some assumptions, of course. So if we assume that our constraints are L smooth and they admit the Lipschitz gradients, then we can use standard descent lemma on this. But of course, these will be approximate convergence guarantees. For less stringent structural assumptions, we can use this Kurdika-Loyashevich inequality. Again, these are standard tools in nonlinear optimization, which we are borrowing here in the context of this gradient-based optimization. So a lot of interesting theoretical advancements that we can still say about the approximation error of our smoothened gradients of the integer correction layers with respect to the hard integer rounding, and how this approximation layer interplays with our approximate feasibility guarantees. So with assumptions on smoothness, you can also obtain 1 over k complexity, non-asymptotic convergence guarantees. But these are still, again, approximate convergence guarantees. A lot of space for improvement in this theoretical analysis, but thanks to familiar gradient-based structure and smoothness approximations, that really like opens doors for some more rigorous feasibility analysis here. So how about empirical performance? We are aiming to solve large-scale optimization problems where traditional solvers fail or they are too slow to be implemented in practice. And in those settings, even for like modest-sized problems, like 100 decision variables, they're integer, and 100 constraints for quadratic cases, state-of-the-art solvers like Gurobi or Skip for nonlinear optimization, over time, they will find better solution than these approximate algorithms. But by pre-training these parametric solutions offline, we are really offloading a lot of cost for the online inference, because now we can, in milliseconds, obtain high-quality solutions with feasibility guarantees on inequalities that can make a difference between real-time implementation. So that's what we are really arguing here. And empirically, we are getting up to 5 orders of magnitude acceleration, which can be really massive.
Yeah, as a helpful question.
Yes.
Okay to ask?
Please, yeah.
Yeah. Okay, so like, two questions. Like, one is like, how do you choose lambda, the term balancing?
That's a crucial question. So in next slide. Yeah. So we did a lot of ablation studies empirically to analyze the effect of the penalty weight. And of course, like if you are putting high penalty weight on the constraints, you are favoring feasibility versus optimality. And for instance, these full lines represent just training the policies with integer correction layers without feasibility projection. So in order to get empirically high degrees of feasibility, where feasibility goes up on the y-axis, we require high values of these lambdas, high penalties. But that kind of significantly degrades our objective values, of course. So after applying these feasibility projections, we can train with way smaller penalties and get the feasibility projection handle the feasibility part. And if we are combining them together, we are getting comparable and sometimes better solutions, especially in the mixed integer nonlinear programming case, than state-of-the-art solvers. So there is this type of trade-off, which we are still trying to understand theoretically, but empirically we are having very interesting results on kind of large-scale optimization problems. I think the largest one was 20,000 mixed integer decision variables that we are still able to train on the CPU within 2 hours, and we train these policies and we still have sub-second inference time. So that's something that I'm really excited about. A lot of opportunities about theoretically answering these tuning questions also can come from applied math community, especially the residual learning in pins. They are putting a lot of effort in adaptive weight tuning based on analysis of your gradients of the loss functions and the loss function residuals and adaptive sampling of your parametric scenarios in regions that are of high error. And we can really interpret this also the regions of like when the active constraints in optimization become active, basically. So this kind of generalized view of scientific machine learning that brings the ideas from applied math, operation research, and controls, I think can create nice opportunities for new methods and theoretical development on those intersections.
Yeah, good. Yeah, I think that I have another question. Like, I think that if I understand correctly, I mean, the rounding part going to deal with the integer part.
Yes.
And then the feasibility going to deal with like continuous. Or like.
Yes, we are updating the continuous variable in the feasibility, but because you have this hard integer rounding in a forward pass, so you are actually embedding that rounding in the feasibility projection layer.
I see. So like, I mean, the feasibility part can also change the integer variable.
Exactly. So like this energy function, like there's the penalty on the constraint violations where the integer variable is represented by this integer correction layer. And thanks to this smooth approximation of the gradients, it allows us to compute the gradient of this function to update the continuous variable. But the continuous variable is passed through the rounding layer in a forward pass.
I see. I mean, it's trained like all together.
Well, actually, in our experiments, what we have done, we trained the integer rounding without projection, and then we use the projection as a post-processing. You could do that, but from the perspective of the stability of the learning and avoiding exploding vanishing gradients, we kind of separated these two. So offline training of the integer correction and post-processing of the projection layers. Thanks. Yeah, thanks for questions, really good. Really relevant for this wonderful work that has been done with Elias Khalil and Bo Tang. You'll be joining your group soon. So yeah, really that was one of my great collaborations that I had in the last 2 years. That brings me to the end of my talk, where I was arguing for scientific machine learning as really potentially unifying methodological advancements that can bring together communities from applied math, operation research, computer science, and controls to develop this type of toolkit that is interoperable and can be practical for important applications in sustainable energy, where we are dealing with large decision spaces, mixed integer decision variables, and hard constraints that are necessary for stability and safety of these systems. So a lot of challenges remain that I have been just talking about two today, but a lot of work on backends, on effective automatic differentiation, dealing with exploding vanishing gradients, ill-conditioned problem, which many of them are ill-conditioned and require careful tuning and modeling. Computational cost of guarantees. There are a lot of interesting methods for verifying this machine learning, but yeah, their cost for uncertainty quantification and hard constraint guarantees is still largely prohibitive for online inference. But I want to end on a bright side, on the opportunities, where I was not talking about potential of solving PD constraint problems or optimal control for PDs that I know many people in the community are start looking at through neural operators. The University of California, San Diego specifically, and other areas. And what I'm passionate about is not only developing new methods and theories, but working on software tools so we can really transition this into practical, viable applications that can really enable the change, the transition in applications that are important more than ever. And hopefully we can enable that by cutting the cost of technologies and making the economical case for sustainable energy. So here I want to thank you very much for being here, and thanks for all the questions.